Okay, so let's continue then. So our mission here is to talk a little bit about medium access control. Medium access control is about how several receivers share a common medium. And now we will talk about structured way to do that, which is called controlled access. And one of the typical examples of this is something called a reservation system. So how does that work? Again, we have a number of users, and in this case we have, as before, capital N number of users that would need to share the channel. Then we organize a transmission over the channel in what's known as a cycle. A cycle consists of a reservation interval plus a number of data frames. The number of data frames can change from cycle to cycle. So we see here in the first cycle here, we have reservation and then 1, 2, 3, 4 data frames, and then another reservation and 1, 2, 3 data frames and so forth. Okay. So how does this work? Well, inside the reservation interval, we have a number of mini slots, and we have the number as many slots as we have users on the medium. And in these slots, we declare whether in which order the data frame will occur. Okay, so let's go through this. We have transmission in cycles, possibly of different lengths. A cycle is a reservation interval plus data frames. The reservation interval consists of n mini slots in which the users reserve the future slots for transmission. Okay, so it could be, for instance, that we have now, say, we have 10 users, and then in this case, user number 2, 4, and say n said, okay, I have a frame to transmit, and then user number 2 for transmit in this slot, user number 4 in this slot, and user number n in this slot. Okay. If we look at the reservation interval here, we see that we have 1, 2, 3, 4, 5 nodes that said they had data to transmit. And maybe this is number 1 and number 2 again, 4 and n. Okay, we need another one here, so maybe all of them that we see here. So from cycle to cycle, those nodes who have frames to transmit inform the other nodes about that by transmitting that information in its mini slot. Okay, so and by doing that, we organize the transmission of the frames here, and we don't have any collisions. Isn't this fantastic? So what's the catch? Well, there is a subtle catch to this, and the reason for this is that during the mini slots here, how do we transmit here? What is the medium access control for these? In this case, it was TDMA, basically that the first user got the first slot, the second user got the second slot, and so forth. That's one way to do that. But there are many variations on how we can do medium access also in the reservation slots here. Okay. So reservation systems come in many different variations. First of all, we have the centralized and distributed ones. So centralized is when we have a central controller that takes care of everything. It listens to the reservation slots, decides in which order of transmission these users will be allowed to transmit, and then issues a grant or a schedule for transmitting. So this is similar to what is done in a LTE system, a 4G system, that the base station listens to the users that are in the cell, which the base station is controlling, which users have data, and then decides which users can transmit and in which order. Okay. Then we have distributed, where each station listens to the reservation transmissions and then determine its transmission slot according to, say, its ID. It knows in which order things would happen. And this could be problematic when reservation transmissions are lost somehow, of course. But there are other problems with this. Okay, so a reservation scheme can also allocate a single slot or multiple slots for a user in a certain cycle. So you can get a different amount of time on the channel, essentially. And this is done in LTE, in 4G, for instance, 5G also. Same thing, that when you get access to the channel, you can have that for a varying amount of time. We also need a medium access control for this reservation interval, and here there are two main ways to do that. Either we do that with random access, for instance with slotted ALOA, or we use some type of static channelization scheme, for instance TDMA. So we'll go through them a little bit more in detail shortly. So let's analyze the efficiency of these systems. Which is rather simple, actually. It's not very complicated. And the thing that makes this not so complicated because we don't have much randomness to take into account. So that's the good thing. So with some assumptions here, that the mini-slot duration is nu times TF. So nu, say that nu is 0.01, maybe 1% of TF, which means that the mini-slot is very small compared to maybe we should use the same colors here. So the mini slot is only 100th of a data. So this is data, and this is mini slot. Okay. We want to make the mini slots as small as possible because this is overhead, right? It's only the blue part which carries data here. Now, suppose the propagation delays are very small, okay, negligible compared to the mini-slot duration. So this is the best we can hope for, actually, so it's a very favorable assumption. Then if all end users have data to transmit, then we can calculate the maximum efficiency of this, or maximum normalized throughput. So what is that? Well, it's essentially how much of the time is for data and divided by the cycle duration. Okay, so essentially rho is equal to data time or data duration over cycle duration, which is this part. Becomes a little bit messy here, but you know, essentially this. So we want a lot of blue, right, compared to the peach color here, or whatever we should call it. Okay, so then if we have n users and they have a frame duration of TF, then the time for the data is n times TF. The cycle duration is n TF plus n mini slots, so n times nu times TF. Okay, and then we just divide by NTF, we get 1 over 1 plus nu. So this is very high if mu is small. Okay. Do you remember what the maximum rho is for unslotted ALOA? Remember? 1 over 2e, or 0.37, right? So if mu is, say, 1% or 10%, this is much better than 0.37, right? So reservation schemes have the potential of being very efficient, but only under these assumptions. So what happens if we relax some of these assumptions? And then we will see efficiency actually decreases. So efficiency drops if only m out of the n users are transmitting, because in this case we have now m here instead of n, otherwise it's the same equation. Okay. So if we then calculate it like this, and then we have n divided by m, so if m here is a small number compared to n, then this is large, and then efficiency is very poor. So say we have 1,000 users attached to the medium, but only 10 users transmit, then this is a factor of 100. Okay, and efficiency is very, very low. Right. So what we can do then in that cases is that we can, perhaps we have if it's so that the blue users, the users that which actually are using the medium, if they have a lot of data to transmit, then can maybe transmit several frames in a shot. Not only one frame, but suppose they can transmit k frames in a row, then we can see that the data duration is then m times tf as it was before, but then also multiply with k, where k is the number of consecutive frames one single user can transmit. Okay, and then we see that the difference here is now k from the previous equations, and we have a k which comes up here. And if we make that k sufficiently large, then we regain the efficiency loss we had as before. But this relies on that there is enough data from each node that we can actually use all these case frames, which is not always the case. Okay, any questions on these efficiency calculations? They're more or less self-explanatory, I guess. When you, we simply just want to, in a cycle, measure how much is the data portion of the cycle portion. Okay, and the key is that we would like to make the reservation period short compared to the data period. Okay. And the one problem we have here, clearly in this case, is that when we have many users attached to the medium, but only few users are active. And this could happen, for instance, if we have, say, electrical meters, like smart metering. In your house, you have a box, and in the box there is a electrical energy consumption meter that reports how much energy you have been using the last hour or day or so. Then in an urban area, you can have many of these, but only few of them are reporting at any given point in time. So here we have a case where we have n is large, but m is a very small number compared to n. Okay. And in these cases, what to do then? Well, what we can do is that we go from having a fixed channelization here, that we have 1 mini slot per user, to have fewer slots here. And then the users have to compete for the slots. Okay, so to make that a little bit more clear, we can have random access reservation systems, which means that we do scheduled access for the data portion, but for the reservation portion, we use random access. Okay, so this is useful when only a small fraction of all the potential users have data to transmit. So when m is much smaller than n. So what we do then is we use L slots for our reservation, where L is less than n, typically much smaller than n. And therefore, it's not guaranteed that we have a slot for all the potential number of users. But we don't need that, because at any given point in time, only a small subset of all potential users are actually trying to use the channel. Okay. So when L must be larger than m, otherwise things will be pretty poor performance. Okay, and M, what is this? Well, it's the expected number of users per cycle. Okay, it could be the same users or it could be different users, but anyways. So, and the reason for this is that random access have a maximum normalized throughput load, which is less than 1. Okay, all of them have, but it's typically much smaller than 1. So if we do reservation with slotted Aloha now with L reservation slots, then we remember that for slotted Aloha, oh boy, what happened? Okay, so for slotted Aloha, so what is rho max for slotted Aloha? Well, it's 1 over E. So 0.37, I think, something like this. Okay, so which means that if we have L slots, we can schedule about L over E or L over 2.7 stations. That's the best we can hope for. So then the maximum supported load for such a reservation scheme is that we need, if we want to reserve L, we have L slots to schedule M users. Okay, like this. And we know that if we have random access of M users into L slots, the best we can hope for is that we can serve L over E users. So we put then L over E equal to M. Okay, that's how to choose L. So L is M times E. That's at least the best we can hope for. Typically, I would choose L to be a little bit larger than this. Okay, but M is L over E, so we just replace M with L over E, and then we get this as our efficiency. Okay, which should then be compared, which is good when E times nu, when this is less than E. Okay, so we should compare this with the E. Here, E times nu, and here we have N divided by M. Okay, so of course there are other random access we could use. We could also use CSMA, we could use slotted Aloha and so forth. And yeah, I think both slotted Aloha and Aloha are used in practice. CSMA perhaps also, but I'm not so sure, to be honest. Okay, any questions on this particular scheme? Crystal clear? Okay. Then let's go on to another scheme, which is polling. And polling has to do with that we have a centralized controller, typically, that is in charge of everything. And there are two ways data can go through, from the primary to one of the stations, or from some of the stations to the primary. So here we have a hierarchy, but this is above the rest in the hierarchy. So we can think of this as the controller. So if the controller would like to get some data from A or B, what the controller does is that it transmits a message to select one of the nodes, in this case node B. So it sends a special message over the medium, and then node B will answer in response to this with an acknowledgement, and then data goes from the primary to B. I said the wrong thing here. There's some data go from the primary to B in this case. Okay, so which means that the primary selects B, B says, okay, I'm ready to receive some data, and then B gets some data, and B acknowledges this. So this is a cycle in this case. So it's initiated by the controller, and then the appropriate station answers, and data is exchanged, and this is acknowledged, and now everything is cool. Now we can start all over again. Another thing is when we have that one of the stations A and B have some data to transmit, then the station first checks with A, do you have any data to transmit? And then A says, no, I don't have any. And then B, the primary then asks B, do you have any data? And B says, yeah, I have. And here, by the way, here it comes. And then A then acknowledges this. And this is a cycle. So this is when data should go from the stations to the primary. And this is for the primary to the stations. Oops. Okay. Questions? So this is common when you have, essentially this is also in a cellular system, where here we have the base station that check that would like to transmit some data to some of the phones here. It has to check whether the phone is ready to receive the data. And the opposite here, when the phones have some data to check. Actually, this is not what's done in 4G, so forget about it. Okay, but one can have this for other buses where this is sort of like a control computer, and we have here sensor stations. That's more normal, I think. Okay. Polling variations, there are different versions here. There's something called exhaustive. What that means is that we transmit the data until the transmission buffer is empty. So basically it's like this, that if, okay. So in this case, when the primary is asking the nodes for if they have data to transmit, the node B here might have a lot of data. Then it can either send all its data here or just a portion of the data. If it's exhaustive, it transmits all its data here, but that could be sufficient or could be a lot of data, and therefore node B then takes the channel for a long period of time, not letting node A get into to play, right? But that, on the other hand, is an efficient way to do this. So it's efficient, but can lead to long delays for those who are waiting for access. We also have time-limited versions where transmission per pole is limited to a certain time. Then we can control delays, but efficiency can also be limited due to this overhead in the polling messages and acknowledgements. Efficiency analysis here is very similar to reservation protocols. So any questions on these polling architectures? No? Okay, so let's continue then. So we have now gone through the random access and controlled access main families for medium access control. So let's contrast them a little bit. We have random access, which is unstructured, loosely coordinated access to medium. So we use collisions and randomized backoff to self-organize. And we detect collisions by the absence of acknowledgements, for instance, or by listening to the medium when we transmit if we do collision detection. It's simple, and it works well when there is low loads, where we basically are not using the medium to its full capacity. Then this works pretty well. Delays are variable, however, and are increasing with the load, which is a drawback. And efficiency is not great for high loads. Controlled access, on the other hand, is structured, well-coordinated access to the medium. So we have very many typically fewer collisions here. However, this comes at a price. Coordination can be costly because of the overhead of all these controlled packets that go back and forth. And for high delay bandwidth products, it could be difficult to do this also, or at least it can be complicated. However, the plus side is that it can be very efficient for high loads, and delays can be controlled in the sense that it can be less variable and upper bounded. So we have better control of this. Delays here could actually be quite small, but they could also be quite long. So they're more unpredictable in this sense. Here they're more predictable, typically longer, but then also typically, well, don't vary so much around the average. Okay. So which one to pick depends. Both of them have pros and cons, so one has to select the medium access control depending on the application and also on the delay bandwidth product, a few other things. So, any questions? Okay, so let's continue then. So we talked a little bit about channelization actually in the very beginning. So this is fixed access to the network, where we divide up the channels into divide up the medium into channels and then hand out channels to users for their exclusive use. Channel resources can be viewed as a frequency time area. So we have time on this axis and then frequency on this axis. So we have some bandwidth and some time. And inside this green square here, we would like to transmit data. Okay, so we would like to have signals which are contained in this time frequency square. And it can be shown that the number of symbols we can transmit here is roughly 2WT. Okay. So the more bandwidth we have or the more time we have, the more symbols we can transmit. It sort of makes sense, right? And the scaling factor is 2 here actually. And this is true at least when W and T becomes large. So the total resource in a time interval T is then proportional to W times T. So if we remember Nyquist criteria early in the course, it tells us that we can transmit at most 2WT ISI-free baseband, that is real valued PAM signals during T seconds, at least as T goes to infinity. Okay. So we see here we have 2WT is the same as we had here, at least when we let T becomes very large. Okay. So hopefully this 2WT here makes sense. If we have complex symbols, QAM, think your Wi-Fi or LTE or something like that, then we use complex symbols, and then we need 2 real symbols for each complex symbol. So we can have here WT, not 2WT complex symbols. It makes sense, right? Because we need 2 real symbols for 1 complex symbol. Okay. So in that case, we can transmit WT complex symbols, ISI free and so forth. Okay, so the name of the game now is that we have this rectangle and we should slice it up somehow into channels and hide out and divide up these channels among the users. So what do? Well, the first thing we can think of perhaps is to divide up the frequency axis into frequency channels. We have the blue, the red, and the green channel here. The channel bandwidth of a particular channel is the total bandwidth W divided by N, the number of channels we need. Okay. So we split the system bandwidth into N frequency channels. Each frequency channel is handed out to one of the users, and then each channel can carry 2W2 times the bandwidth, which is W divided by N, T symbols during T seconds. Or the symbol rate we can get is 2W divided by N. Okay, so this is the symbol rate in each of these. Okay, and of course, if we take N times RS, we get back to this 2W complex symbols per second. Okay. So we just split up the channels like this. So this frequency division, you can think of this as, for instance, a regular broadcast radio, where you tune in to a certain frequency and then you listen to that program. Like P1 is here, P2 here, P3 here, mixed megapole is over here and whatnot, right? And it's there forever, more or less. Not forever, but it's there for extended period of time. And they have exclusive use to these frequency channels. We can also divide up time. So here we split the time axis into n time slots. Slots are handed out to users in a round robin fashion. So here user number 1, 2, 3, and then the next time slot we're back to green, red, and then blue, right? And we keep on doing this indefinitely. So here we get different time slots. So each time slot can then carry 2w, and now we split the time axis into t over n, symbols during t seconds. So the symbol rate rs is equal to 2w over n, which, by the way, is exactly the same as we had in frequency division. Which should not be surprising. We have sliced up the cake in another way, but the cake is what it is. And if we split up the cake in equal parts, then nothing has really changed. Well, maybe somebody preferred the top layer of the cake and the lower layer, but that's not part of this model, right? Okay. So nothing really changes here. So time division and frequency division has the same properties that we cannot gain by choosing one or the other. So it's practical things that determines whether we use TDMA or FDMA. In many cases, we actually use a hybrid between these two. So for instance, modern 4G and 5G systems is built on a hybrid between TDMA and FDMA. Then there is another one which is called code division. This was popular. This was the access method used in 3G and also used in some military applications and so forth. And basically we separate users also when they can be separated also when they use signals that overlap in time and frequency. And so this is exploited in these code division schemes. However, one can show that the fundamental limits is the same. So we don't gain anything by incapacity by using code division. It's just another way to slice the cake. Okay, so the choice between time division, frequency division, code division is based on other factors than data rate. Simplicity, other things, right? And in practice also we need guard intervals in time and or in frequency in order to fully separate channels. This has to do with propagation delays and also by problems of having ideal band limited filters and so forth. So there will be some interference going from one channel to other channels, and we need to control that. And one way to do that is to make sure that we have guard intervals between the channels. Practical systems are often hybrids, and code division is also used, for instance, in 3G, and Bluetooth also uses a type of code division called frequency hopping. Questions? Okay, so a little bit of pros and cons with static channelization. Pros is that it's efficient for constant data rate services. That is, when think of broadcast radio, if the channel is always transmitting, this is a great case for doing channelization. However, if we have a situation where channels are not always transmitting, then it's inefficient, right? Because you have allocated a channel to a user which is not using the channel, then that resource is basically wasted. So the cons with the static channelization is that it's inflexible when the user have data rates which varies in time. So sometimes they have data and sometimes they don't. Then it's inefficient to use static channelization. So for data traffic, the type of data that we are talking about mainly in this course, like internet traffic and things like this, is typically much more attractive to use this dynamic medium access control, either like a random access or controlled access methods, the things that we talked about earlier today. Okay. Any questions? Because this more or less now ends the section on medium access control. And now we will look into, what should we say, more practical schemes and see how they use things that we have learned about retransmission protocols and medium access control schemes, and see how that works in some of the practical systems. So the first practical system we will look at is different LAN methods. So what is a LAN? LAN stands for local area networks. And if you remember at the beginning of the course, we said that these are physically small networks. Distances maybe up to a kilometer or so, where we use a broadcast medium typically. So then we need medium access control. So hosts could move around. We can think of Wi-Fi as being a LAN standard. Each network interface card is given a unique physical address, at least in theory. We remember that we can actually program these, but typically they should not, they should be unique. Something that you get when then the card is manufactured and should never change in time. Transmission on wired medium are typically close to error-free, and therefore we don't need very sophisticated error control techniques for those. However, wireless local area networks are quite affected by error, so here we need some type of error control. And LAN protocols are typically placed in the link layer. Okay, so it's data link control and medium access control, retransmission protocols and medium access control protocols, for instance. So now, if you remember, in the beginning of the course, we talked about the OSI model. So the OSI model is this theoretical construction where everything is very clean, everything is well-defined protocols and interfaces between them. So these are theoretical constructions. There are not many practical protocols which are OSI protocols. However, there are many protocols which basically which are inspired by this. And now we will talk about a set of protocols called IEEE 802 protocols. And these specify data link layer and physical layer. Does not specify the network layer, so we're still looking at the lower layers. As a matter of fact, the IEEE family 802 protocols specify a link layer control, a number of medium access controls, and a bunch of physical layers. Okay, but there is actually only one link layer protocol, and that's called LLC for logical link control, and it's called 802.2. And the medium access controls here, we have a CSMA collision detection protocol, we have Wi-Fi, we have token ring, and we have a bunch of others. They have different numbers. You see 3, 11, 5, and so forth. And then under, say, Wi-Fi here, the .11, there is 5 physical layers or something like this. Not all of them are used, of course, but there is basically one main layer which is used nowadays. But for historical reasons, there are different physical layers that during some period in time were popular and maybe lost in popularity lately. So now almost all Wi-Fi networks use the same type of physical layer with variations, actually. Anyways, okay. This medium access control, what they do is that they provide a service. So these provide a service up to the logical link here. That's how protocol works. What kind of service? Well, it's a very simple service. It's an unreliable datagram service. So datagram is just another word for packet. So it basically accepts packet here and does its best to transmit those. But, you know, no guarantees. Unreliable. The link layer then refines a service. So it provides a service up to the layer above it. And it can enhance this MAC service and can provide 1 out of 3 types. An unacknowledged connectionless service. And this is the mandatory, and actually this is the one which is most heavily used in practice. So basically it does nothing to refine the MAC layer service. Or it can provide a reliable connection-oriented service, so which means that basically has to implement a retransmission protocol, like a stop and wait or something like this, go backend perhaps. Or it can also provide a type 3, which is acknowledged connectionless service. So this is not a ARQ protocols that we have talked about. We talked about, stop and wait, go backend, and selective repeat. All of them are connection oriented, where you need to set up sequence numbers and so forth between the sender and receiver. But one can also have a scheme where you basically transmit the packet, and then in the acknowledgement you identify which packet it is without using predetermined sequence numbers between the sender and transmitter. Okay, now out of all of these, the one which is used in practice most heavily is the type 1. LLC supports many different networks layer protocols up here. So here we could have IP, for instance, above this, but we could also have many other protocols here, network layer protocols. Okay, so if we look at then the protocol structures here a little bit, okay, so of course this is a lot of details about, because if we look at practical protocols, we see a lot of the nitty-gritty details and sometimes hard to see the overall structure of things. But I think it's instructive to look at this also. But then you might wonder in the exam, will I ask how many bytes are there in the source SAP address for a LLC PDU? I will not ask that, right? So these are not important numbers. It's important that there is such a field and what the interpretation of it is, but not how many bytes there are in each of these. So the link layer protocol data unit. So the link layer protocol data unit consists of some header and then some payload. And this payload came from the network layer above. Okay, and the link layer header is 2 addresses, destination, source, and then some control bytes needed for internal working of the LLC protocol. This SAP addresses, service access point, identifies the protocol entity above the link layer layer. So instance, it could be like, for instance, this particular protocol, which is 42, and some other protocol, which is AA. Okay. This subnetwork access protocol is a mystical name. SNAP is what people usually say. This is actually used quite heavily in practice. And it's used to multiplex protocols that don't have their own SAP addresses. So if SNAP is used, actually the LLC header is extended with 5 bytes. So here we see 1, 2, and 1 or 2 bytes here. And suppose it's 1, 1, 1, and then plus 5, then these are 8 byte long now, if SNAP is used. Okay, the MAC layers protocol data unit consists of the payload that it got from a layer above, which is, this is the payload it got from above. So this goes down here, and then the MAC layer just puts on its own header and some frame checksum, typically like this. So this is encapsulation, just as we saw very early in the course. So I think this is a good point to break. So we will continue now to talk about the 802.11, IEEE 802 family of protocols, and we will talk about this particular medium access control, which is also known as Ethernet, and then we will talk a little bit about Wi-Fi also, just to see how these protocols work in practice. But let's continue with Ethernet when we meet on next time on Thursday. All right.